soil profiles, something like this, right? So we have this big profile right here. We have something like an A horizon, B horizon, C horizon, and we'll put the parent material horizon on here down at the bottom as well. This is the R horizon. And so, just to remind you, R is parent material. R stands for rock, but the parent material could also be aeolian sediment. It could be glacial till. C is the saprolite. And so that's the parent material, but just with some material removed, perhaps some easily weathered minerals. So if the parent material were a granite, the saprolite would be missing things like biotite. And the saprolite is going to have the same volume as the parent material, but because of the loss of those minerals, it's going to be a lot weaker. It's not going to have that same structural integrity because all of that hard stuff is replaced by pore space. Above that, we have this B layer. Yep. And this B is the B horizon. And that's a zone where material can be concentrated or leached. And this A horizon up here has the most organics and humic material and so forth. And, you know, if there's some kind of leaf litter or something that's sort of scuzzy on the forest floor, that can be an O horizon. And so we talked about this whole thing as this weathering reactor, or weathering engine, in which this front, the soil profile continues to extend down by wearing away at that rock and converting the rock to saprolite. That saprolite can convert into the B horizon and so on and so forth. And so what we really need to understand this whole process and to be able to model it is something we call a soil production function. So some kind of mathematical representation that tells us how quickly is this rock worn down and turned into soil. Fortunately, we have a couple excellent examples of soil production functions that people have come up with. And here's the idea. I'm going to start out with this exponential decline model. Yep. There we go. All right, that's a better underline. So in the exponential decline model, what we're saying is that soil production rate is high rate when soil depth is low. And so you can think of here, at this end of this figure, we're going to have something that's just like a itty bitty set of like A, B, C, R. On the other hand, on this end, we're going to have some sort of really big, you know, A, B, C, R. So there is going to be much larger, much deeper to the soil, much larger soil horizons. And so something like this, right over here, is going to have a low soil production rate. All right, so why do we see this? So the answer here is that we have this high rate, or actually the observation here is that we have a high rate of soil production under thin soils. We have a low rate of soil production under thick soils. There are a couple reasons that are put forward to explain this. One reason is the fact that under these thin soils, we can actually affect the bedrock and damage it with frost. But under these thick soils, they might stay insulated all year, so it could be insulation from frost damage. And so that works in some climates that have winter and have some significant temperature swings, but it might not work in all climates. It might not work very well in places that have consistently low temperatures like Antarctica, off of the Antarctic Peninsula, where it's just cold enough that maybe the water's always ice. It might also not work in places like the tropics and the tropical lowlands, where there isn't really ever frost in the first place. So, what other processes could there be? Another one goes back to what we were talking about with weathering. So, chemical weathering reactions. So at these shallow depths in the soil profile, I'm just going to draw another soil profile right here, we can have fluids that will infiltrate into the surface and flow through and flow laterally. And that can happen pretty quickly. So I'm just going to put H2O plus solutes. It's a little bit harder for water to go farther down, and it takes longer for that to happen. And so because of that long residence time, this is less saturated with solutes than this one is. So this path is deeper, longer res time, more saturated. And so what do I mean by solutes, and why is that important? So let's imagine that we have water that's flowing past something that can dissolve. We often talk about calcium carbonate, so let's just talk about that for the moment. So if the water starts to pick up calcium carbonate by dissolving it and create the calcium and the carbonate cation and anion in the water, the rate at which that material can be dissolved is proportional to how undersaturated the water is. But at some point, that water is going to be carrying as much of a load of calcium and carbonate as it possibly can, and therefore it's not going to be able to dissolve material anymore. And likewise, if there is a long residence time, that means that we're not going to be seeing other very steep chemical gradients, like this example with the calcium and the carbonate, that could cause there to be weathering reactions. So, because of that, and because of similar arguments that can be applied to biological processes as well, we actually don't see as high weathering rates in deep depths as we do near the surface. So, weathering high and weathering not so high. So, with that, we might think that this exponential decline model is pretty good. But let's just think about one thing. So I was talking about frost, and I was talking about chemical reactions that are mediated by water, and both of those require water to be present. But what happens if we essentially just have something like this, which is bare bedrock? So if the rainfall, let's see, I'm going to draw my little cloud here. So if some raindrops, those ones are a little better, yeah, fall onto a nice patch of soil, they can soak in and cause chemistry to happen, which means weathering. But if they instead fall, and here I'm just going to draw another little cloud. There we go, a little poofy guy. If they instead fall on some sort of exposed rock at the surface, that water can just run off the sides, and it won't actually do very much to weather it at all, so there'll be no possibility for weathering to happen chemically. And there aren't, especially if there's a very solid rock, there's not going to be much water to freeze and expand in the joints between the different chunks of that bedrock piece, and therefore it's going to be quite difficult for that rock to become eroded or weathered. So because of that, we have this hump function. And so basically bare bedrock has a low weathering rate. As we go up the curve, we get to a maximum. And then as we go down the curve again, we go to lower and lower weathering rates. So that gives you this idea that, deep soils will continue to weather consistently, but shallow soils won't. Deep soils will continue to weather consistently. Shallow soils will weather at the fastest possible, and the places with little to no soil at all will weather quite slowly, similarly to a very, very deep soil depth.